Greetings, everybody. So let's look at this problem, which I found from our assignment on my math lab. And it says this. Considering this function on this interval, find any absolute extrema. So by that, they mean that I'll consider this function and I will look only at it as it spans the x-axis from negative root 29 to root 29. Okay? And I'll try to find any points that visually, as far as vertical positioning on the graph, are the absolute highest or lowest. Okay, so that's kind of a simple way to say it. In fact, I'm going to spoil this question by just showing you what the graph looks like before we talk about how to figure this out. So here's what this graph looks like if I look at it from negative root 29 on the x-axis, which is this point here, over to root 29 on the x-axis. I see that there are, in fact, as far as vertical positioning goes, one point that is absolutely higher than any of the others and another point which is absolutely lower. Okay, I can't really tell where the point is. I could give you a rough guess where that point is, but I can't tell you with absolute precision that it's, say, root 58 over 2. Okay, so if that's the answer, that means that this absolute maximum point right there is located at an x-coordinate of root 58 over 2. Okay, so that's what we're after. I, of course, haven't showed you how to do this yet. I've just told you that that's the concept behind what we're trying to do. I've posted some steps to this problem, how you would, in any case, find the absolute maximum or minimum points for a function on a closed interval. And you could read through this if you want to, but I'll at this point work the problem and I'll maybe come back to this a little bit. Okay, so here goes. We have this function on this closed interval right here. Now I wrote that a little bit differently. I noticed in the statement of the problem they put negative root 29 comma root 29 with brackets around it. That's called a closed interval. All that means is that I'm considering this function as far as the x is between negative root 29 and positive root 29 inclusive. You know, these are less than or equal to symbols. We're including the plus or minus root 29 in our consideration. Okay. One thing real quick though, this closed interval, it might be arbitrary. It's just something that's given to you. It's the window through which we're going to look at this function. But I noticed in this case that if we went outside of this interval, if I had an x bigger than root 29 or smaller than negative root 29, it would give me a complex number in that function. Okay, so you might see, like, say I had root 30, which is bigger than root 29. If I square it, I get 30, and then when I take 29 minus 30, I get negative 1, and I end up with square root of negative 1. So that at least wouldn't be a real number, and it's not going to be something like this that we would look at and say that I have a maximum and a minimum. Okay, so that's why this one is that way. This just happens to be the domain of that function. Okay, but nonetheless, here goes. Our first step in solving this kind of problem is to locate these things called critical points. Okay, critical points are any values of x where the derivative is either 0 or undefined. So let's start the problem this way. If I'm going to find the critical points for this function on that interval, then I need to figure out where the derivative is 0 or undefined, and to do that I need to find the derivative. So that'll be my first order of business. I'll say this is step 1a. So here's my function and here's the derivative. It's a combination of the product rule and the chain rule. The product rule says that if I have a function a that's like a times b, then the derivative is a prime b plus b prime a. So that's what I have there. But in order to find the derivative of 29 minus x squared to the 1/2 power, I have to use the chain rule. So that's what you see here. So there's our initial step for the derivative with the rules that are applicable. And if I simplify that, I'll get this. Now, throughout this problem, I've chosen not to write square roots like that, and I've written everything as the 1/2 power. Okay, which, you know, that would be more helpful for us anyway. So that's step 1a. I have my derivative. What's the next step? well, I'll say step 1b. Now, I remember when I was looking over at that procedure that I showed you a second ago, it says find the critical numbers. Find out where the derivative is either 0 or undefined in the open interval. Okay, meaning excluding the endpoints. So I'll do this. Let's start by figuring out where the derivative is 0. So here's the derivative that I just found in step 1a. I'll set it equal to 0. I'll solve it by moving this term to the right-hand side of the equation. I'll multiply both sides of the equation by 29 minus x squared to the 1/2 power. I'll get this. But when you multiply like bases, you add the exponent. So I'll get 29 minus x squared to the power 1/2 plus 1/2, but that's 1, so that's this. Then I'll collect the x terms together. I'll divide by 2, and I'll solve by the square. I'll solve for the square by taking plus or minus root. Okay, so our solutions, the points where the derivative is 0, is going to be plus or minus root 29 over 2. I noticed the answer on my math lab has that number rationalized. Okay, and I won't go into what rationalizing is because it's something you've probably seen before. I wouldn't mind clarifying or explaining it if you ask me, but for now I'll say if we rationalize that, we'll get root 58 over 2. Okay, those are some of the critical numbers. The critical numbers are all the points where the derivative is either 0 or undefined. And so far, I've found 2 points where the derivative is 0. Okay, so I've got 2 critical numbers so far. What about undefined? Let's see, like, here's your derivative. I just figured out what it takes for it to be 0. What about it being undefined? Well, this could be undefined in this sense. Like, I see that there's this fraction, and I know that if you divide by 0, that is undefined. Okay, so I notice further that if x was either plus or minus root 29, when I square it, I would get 29, and 29 minus 29 is 0. So it looks like those would be critical numbers also, because the derivative is undefined at plus root 29 and minus root 29. But the fine print goes like this. When we solve this kind of problem, we're given a function on a closed interval, meaning where we consider that the endpoints are in play, but the critical points have to be inside the endpoints, meaning that the endpoints are excluded from being in play. So, all right, it might be true that our derivative is undefined at root 29 and minus root 29. Okay, that might be the case, but those numbers are not in play as far as finding the critical numbers. All right, so we just have 2 critical points. They are plus root 58 over 2 and minus root 58 over 2. So that concludes step 1b. Now, where are we at in this? So I did step 1 basically. I find the critical points in the interval root 29 negative to root 29 positive, excluding the endpoints. Okay. Step 2 says to do this. Evaluate the function at the endpoints of the interval that you started with and at any critical points you found in step 1. Okay, so let's look at that. So I need to evaluate our original function at the critical points, root 58 over 2 plus and minus, and the endpoints in my original interval, root 29 plus and minus. So I'll just do that on this table. Okay. So in here, you just have to do the math. You take these numbers, you put them into the original function, not the derivative, okay? Because at this point, I'm trying to see where are the points on the curve and how do they compare with each other, all right? So I take my numbers here and I put them into f of x, the original function, right there, and I do the math. Now, for the sake of this video, I did not write out the calculations, but here's what you'll get. You'll get 0 if you put negative root 29 into the function. You'll get negative 29 over 2 or negative 14.5 if you put negative root 58 over 2. You get 29 over 2 or positive 14.5 for root 58 over 2. And you'll get 0 for root 29. So that's the left endpoint of my original interval, the right endpoint of my original interval and the critical numbers. Okay? Now, here's what that accomplishes for us. Your highest and lowest points of this curve on that interval must be on this table. There are lots of other numbers we could have plugged in, but the highest and lowest points have to be here. If you look at the endpoints and the critical numbers, they have to be there. So your absolute maximum is whichever of these is the biggest. And your absolute minimum is whichever of these is the smallest. So you just compare. What's 0, negative 14.5, 14.5, and 0? Which of those is the biggest? That would be this point right here. Root 58 over 2 for x and 29 over 2 for y. And which of these numbers is the smallest? That would be this one. Negative root 58 over 2 for x. Negative 29 over 2 for y. So that's where your absolute maximum and minimum are. They're on the table. They have to be there. Okay? All right. Now, I noticed that there's a little bit different way that I could say this. Here I've given you points on the curve, and it's like this. I'm saying, do you see this point right here, which as far as vertical positioning goes, is at the top? That point right there has an x-coordinate of root 58 over 2 and a y-coordinate of 29 over 2. But we often just say that the y-coordinate is the maximum, because the y-coordinate is what measures vertical positioning of the point anyway. Okay, so I noticed that I could state the answer like this, but my math lab has it a little bit differently. It says the absolute maximum is the y-coordinate located at the x-coordinate. But you see the numbers are the same. It's just a little bit different way of describing the answer. Okay? All right. So that's everything for this sort of problem. All right? If you want to classify this sort of problem and recognize other problems in the assignment that are like this, it's that we're given a function on a closed interval. A closed interval includes the endpoints. And from there, if that's what we have, we can find the absolute greatest and smallest point with this procedure every time.